Alright, so here's that video that you guys have probably been waiting for. Sorry, it took me a while to get to. I'm going to also try and get through this quite fast so that I don't have to do it anymore. So, Chapter 4 Review. An object moves along the x-axis so that its position at any time t is greater than 0 is given by x of t is equal to s of t. So position. Find the velocity of the object as a function of time t. Or I guess just t. So we're just going to find the derivative of s because the derivative of position is velocity. So velocity will be equal to, take the derivative of the outside function, which would be sine. So the derivative of sine is cosine. The inside will stay the same. And then we're going to have to multiply by the derivative of the inside function, which is this expression inside here. The derivative of a constant is 0, and the derivative of negative 4t is negative 4. And yeah, there you go. That should be it. If you want to write it in standard form, probably put the negative 4 out there, but that's good right there. Same thing here, so we're going to find the derivative. So v will be equal to, I'm going to need the product rule. Product rule is needed because I have a function of t multiplied by another function with t. So let's do the first term multiplied by the derivative of the second term, which would be cosine of pi minus 9t multiplied by negative 9, because I have the outside function that I'm taking the derivative and the inside function which I'm taking the derivative of as well. So the first times the derivative of the second plus the derivative of the first, which would be 1, times by the second, which would be sine pi minus 9t. And again, if you want to write it in a more standard format, you can move that negative 9 outside there. Okay, find dy dx, find the derivative. So for me, I would rewrite this as 7 minus 4x to the negative 1/2. And then the outside function involves using the power rule, so I'll drop that down. So it's going to be negative 1/2. The inside will stay the same, and then decrease that by 1, which would make it negative 3/2. Now I have to multiply by the derivative of the inside, which would be negative 4. And then if you simplify just here and there, you can take the negative 4, multiply by the negative 1/2. That would make it positive 2. And then you can put this into the denominator, so 7 minus 4x raised to the 3/2 power. And I think that's right. Let me double check the key 1 second. So number 3, 2 over, yeah, there you go. Okay, let's go ahead and do number 4. So for 4, we have y prime, and that's going to be equal to, I'm going to write this as cosine of pi x minus 15, and then this being raised to the 5th power. So I'm going to use the power rule, so I'm going to drop that down, keep the inside the same, and then this is going to drop to the 4th power, and then we got pi minus pi x, so pi x minus 15. Then we're going to multiply by the derivative of the inside, which would be derivative of cosine, and that's going to be negative sine. Inside will stay the same. And then I'm going to multiply that by the derivative of the inside of the cosine, which would be pi, so times by pi. And then if you want to simplify, we've got negative, we got, so negative 1, we got pi and 5. If you want to slip those out in front, you can do that to write it more in standard form. Alright, this one right here, this one's going to require the product rule because we're taking the derivative with respect to theta, and we have a function of theta here and a function of theta here, so we need the product rule. So r prime, or dr d theta, r prime will be equal to the first times by the derivative of the second, and that would be, well, if you think about it like this, you can write it like cosecant theta raised to the 1/2. So the derivative of the second is going to require the power rule. We're going to drop that, decrease, inside stay the same, and then multiply by the derivative of the inside. So times by we'll do 1/2 cosecant to the negative 1/2. How about we write, we'll just write it like this, cosecant theta to the negative 1/2, because we decrease that by 1, times by the derivative of the inside, and the derivative of cosecant theta would be negative cosecant theta cotangent theta. So this again was the first term, multiply the derivative of the second term, plus the derivative of the first function, which would be x, times by the second, so square root of cosecant theta. Okay, now as for simplifying, to get what they have in the back, the calculus is all done right now, so this looks great. If you want to simplify it like how it is in the back, well, you obviously have the 8 and the 2, that would make that 4 theta. Okay, now if you think about this right here, this is a cosecant to the negative 1/2, and this is a cosecant first power. And these are the same. It's like if I were to say, oh, also, I'm going to bring this negative out here. So it's going to be negative 4 theta. So if you use the property of exponents, if you have, let's just not even say x, let's say a to the third power times by a to the negative 4 power. These powers have the same base, so you can add the exponents. So this would end up being equivalent to a to the negative 1 power. It's the same concept here. Our base is the same as here. This is negative 1/2, this is 1, so you can add the exponents. So negative 1/2 and 1 would just be 1/2, which would just be the cosecant, the square root of cosecant. So I'm just going to say square root of cosecant of theta, cotangent of theta, and then plus the 8 cosecant of theta. And then last thing, I think what they do is they factor out, do they do anything different there? Trying to think what I can do here. Yes. Oh, that's why. I did not put my square root over there. There we go. That's what I was missing. Here and here, because both terms on the sides of the addition have a square root of cosecant, and they both have a factor of 4. I think in the answers they take out a negative 4 and cosecant theta, and that's how they get the answer in the key. Alright, moving on, finding y double prime. So y prime will be equal to, this is a constant, I'll just keep the constant. I guess I shouldn't say constant, it's a coefficient. So the coefficient of this expression stays there. Now you have to take the derivative of tangent, and then you'll take the derivative of the inside. So the derivative of tangent is secant squared, keep the inside the same, and then times by the derivative of the inside, so times by negative 9. So if you simplify just a little bit, there's that and that. That's all these coefficients, so that's going to be negative 9/4. Secant of negative 9x minus 4 squared. So I'm going to do that for the sake of the next derivative, because I'm going to find y double prime. And y double prime is going to be equal to, I'm going to use the power rule because that's the outside function. The function is squared. So drop that, that becomes negative 9/2. So negative 9/2. And then I'm going to keep the inside the same. So it's going to be secant of negative 9x minus 4. And then that's going to be decreased by 1, so it's just going to be to the first power. Now I'm going to multiply by the derivative of the inside, so the derivative of secant, so times by secant of negative 9x minus 4 tangent of negative 9x minus 4. So there's the derivative of secant. Again, the inside stays the same, and then multiply by the derivative of the inside, so multiply by negative 9. So times by negative 9, and then 9 times negative 9 times negative 9 is positive 81. So you can make that simplification, and then you can multiply these together, so you get secant squared. So we'll say 81 over 2 secant squared of negative 9x minus 4 tangent of negative 9x minus 4. And I think that should be good. Okay, so find dy dx by implicit differentiation. If applicable, express the result in terms of x and y. So take the derivative of x cubed. So that's going to be 3x squared equal to taking the derivative of cotangent of y. The derivative of cotangent is negative cosecant squared of y, but I'm going to have to multiply by y prime because of implicit differentiation, and that's the derivative of the inside. And then just solve for y prime, so we're going to divide both sides by negative cosecant squared. So we get 3x squared divided by negative cosecant squared of y. And there you go. Okay, so for this one, take the derivative of 7y, which would be 7, and then we multiply by y prime, and then minus 14x equal to 1, I think. And then solve for y prime. So 7y prime will be equal to 1 plus 14x, I think. And then divide by 7, so y prime will be equal to 1 plus 14x divided by 7. Alright, given x squared minus y squared is equal to 17, find the line that is normal to the curve. So a line that is normal requires us to have slope m, y1 and y2, y1 and x1, which we already have, so we just need to find slope and put it into a normal line. So let's find slope, so take the derivative. So it's defined implicitly, not explicitly, so we have to use implicit differentiation. So 2x minus 2y y prime equal to 0. The 2's don't really matter here. So let's say we add this to that side right here to keep it all positive. So x will be equal to y prime. Divide by y, so y prime will be equal to x over y. And at the given point, it will be equal to negative 9 over 8. And that means that the slope of the normal line then, remember that this would be the slope of the tangent, slope of the normal line would be positive 8 over 9 because it's the negative reciprocal. And so our normal line will be y minus 8 equal to our slope times by x minus x1, which would be plus 9. So there's our normal line. Alright, find dy dx. I'm going to write this as if it were 11x to the 1/6, and I'm just going to use the power rule. So y prime will be equal to 1 over 6. Inside stays the same, minus 1, or in other words, I will subtract 6 over 6, which would then be equal to negative 5 over 6. Don't forget to multiply by the derivative of the inside, which would be 11. So there you go. You can just put this, multiply that here, so 11/6 would be the coefficient. Alright, find the derivative of y with respect to the appropriate variable. So we're defined in terms of y, so the appropriate variable would be x. And so here's a coefficient, so y prime, we're just going to keep the coefficient. Now here, take the derivative of sine inverse of that, so then the derivative of arcsine is going to be the square root of 1 minus the function squared. And then I'm going to multiply by the derivative of the inside, which would be 15x squared. So simplified together, I think that's just 45x squared divided by the square root of 1 minus 25x to the 6, if you were to square that expression right there. Derivative of arc cosecant of 6 over t. I'm going to think about it like arc cosecant of 6 t to the negative 1. So the derivative of cosecant, so y prime will be equal to, on the denominator we'll have the square, we'll have the absolute value. how do I want to write this? I'll say, yeah, 6t to the negative 1 times by the square root of, we'll say 6t to the negative 1 squared minus 1. That's all in the numerator. In the numerator will be the derivative of the inside because of the chain rule. So it's going to be negative 6t to the negative 2. And then as far as simplifying goes, you can simplify this denominator, which will then simplify that right there. So let me do like a sidebar sort of thing. So 6t to the negative 1 squared is just going to be 36t to the negative 2 minus 1. So again, this is kind of just what's happening underneath the radical. And then that's the same thing as 36 over t squared minus, I'm going to say 1 over 1, or another, I'm going to say t squared over t squared because we want a common denominator. So then here, this will just become 36 minus t squared over t squared because we combine the numerators, or we add them. And since we're taking the square root, this right here will just become t without the square root. Okay, so, but that would be in the denominator here. So it's like if you had the t in the denominator here, and then I'm going to move it up to the numerator, which would make it t to the negative 1, which I could then add with this right here, which would make it t to the negative 2. Now, to simplify those, since it is absolute value, I'm just going to drop the absolute value and say that t is always positive, therefore we don't have to worry about that. So again, if I were to take everything that I just simplified, I have negative t squared, 6xt to the negative 6t to the negative 2, there we go. And then we would have 6t to the negative 2 again. So that reason being, one more time, is that this is all under a square root. This right here, I could take the square root of that. So it would be as if it would be the square root divided by t instead of the square root of all of this under t squared. So again, one more time, we're taking the square root. Well, the square root of that is t, so then it becomes square root on top over t. I'm going to move this up to the numerator. That's going to be t to the negative 1, but there's already a t to the negative 1 over here, so then I can add them to make it t to the negative 2. And then I have the square root of 36 minus t squared, which then those cancel. So then I get y prime is equal to 1 over the square root of 36 minus t squared. ... algebra. There you go. Okay, and yeah, the algebra was kind of just explained over here. Okay, okay, 13. Cotangent in arc cotangent. So the derivative of arc cotangent. So we'll say y prime is equal to, that's going to be, so we're going to say y prime is equal to negative 1, because that's cotangent, arc cotangent that is. Okay, and then we're going to have the 1 plus the square root of t minus 4, and that's going to be squared, times by the derivative of the inside, and the derivative of that, you can think about it like being raised to the 1/2. However, if you guys are catching on to if you guys remember that the derivative of the square root of x is equal to 1 over 2 square root of x. So the derivative of the square root of f of x is going to be equal to 1 over the square root of f of x times by f prime of x. So I usually just follow that little shortcut instead of using the power rule. So the derivative of that would be 1 over 2 square root of t minus 4 times by the derivative of the inside, which would just be 1. So then this right here, if you square that, the radical and the exponent cancel, which means I can combine the 1 and the negative 4. So then I can say t minus 3 instead. And then I can move the 2 out here, and then I would have square root of t minus 4, and that's all over negative 1. Okay, Let's see. Particle moves along the x-axis so that its position at any time t is greater than 0 is given by x of t. Find the velocity of the indicated value. So just finding velocity, so we'll say v of t is equal to the derivative of tangent of arc tangent is 1 over 1 plus t squared. In this case, that's going to be t squared over 9, because we're going to square this inside part. Then we're going to multiply by the derivative of t over 3, which is just going to be 1/3. You can think about it as 1/3 times by t. The 1/3 is just the coefficient. Okay, honestly, if you just plug in 2 right now, you can do that. You can just go ahead and plug in 2. There's really no need to really simplify the expression, especially in this case. I mean, you don't really have to anyways, but especially in a case where you're just going to plug in the value, you can just go ahead and start plugging it in. So we'll say v of 2 is equal to 1 over 1 plus 4 over 9 times by 1/3. That's going to be 9 over 9 plus 4 over 9, which would be 13 over 9, I believe. So we have 1 over 13 over 9 times by 1/3. This expression I'm going to keep change flip, so it's going to be 9 over 13 times by 1 over 3, which will then be 3 over 13 because those simplify to be 3. And there you go. Find the equation for the tangent to the graph of y at the indicated point round to the nearest thousandths. Okay, so y prime would be equal to, so the derivative of secant is going to be equal to square root of x, and it is just x, so this is actually one time where we don't have to use the derivative, we don't have to use the chain rule. Square root of x squared minus 1, okay, and then we are going to do this at, so we're trying to find a tangent line. So again, tangent line is going to require m, it's going to require y1, and we have x1, which we already have. So let's find, I guess since we already took the derivative, let's find m. So m is going to be equal to y prime at 5. So that's going to be equal to 1 over 5 times by the square root of 24, because if we plug in 5, that's 25 minus 1. And then 25 is divisible by 4, so 4 times by 6, and then you can take the square root of 4, so that's going to be 2, so then we multiply that by 5. So then with some algebra, that's just going to become 10 square root of 6 as your slope. And I think you could just plug into a calculator, that's fine, to get a decimal. Okay, now we need to find y of 5. So we're going to plug that in, secant negative 1 of 5. Since we can't plug that into a calculator because I don't think many calculators have the function of arc secant, they just have the arc sine, cosine, and tangent. We're just going to do this by hand. So if this is what y is equal to, I'm going to reverse the operation of secant on both sides. So then I'll have secant of y is equal to 5. I'm going to put over 1 because remember that secant is a ratio of two sides. Specifically, it's the ratio of the hypotenuse over the adjacent. So this length right here represents, so in a right triangle, this would represent the hypotenuse and this would represent the adjacent side. So if you were to draw a triangle like such, you'd have 5, 1, and this would be the angle y. And so now here, I could state it in cosine terms. So let's say cosine of y is equal to 1 over 5, and therefore I can use arc cosine on both sides, and I get y is equal to arc cosine of 1/5, which then means I can use this in my calculator. So remember, you'll get y minus y1, which is this expression right here. So put that into your calculator, equal to m which is what we have here, times x minus x1, which was 5. So don't really have a calculator accessible right now, so you can go ahead and do that right there. Hopefully I don't need a calculator for the rest of the problems. Okay, so this one, I'm probably going to go into a little bit more explanation than is really required. That being said, it's actually really simple. So, but I'm going to give it probably way more explanation than I think would be required. That's because I think it's important to know for like the AP test. So this expression right here, it's basically just saying the derivative, so of the inverse of x. Yeah, so this is just the derivative of the inverse of the function. So to kind of just give a kind of more visual representation, say you have two functions and they're inverses, which means they would be reflective of each other over the line y is equal to x. And because of that, they share corresponding points, inverse points, where if this was a point a comma b, this function, the inverse function, would have a point of b comma a. And we should have learned earlier that at these given points, these corresponding points, their slopes are not negative reciprocal, just reciprocal. So we'd have a line like this, and we'd have a line like this. So make sure that first that you don't use the negative reciprocal like you would a normal line. And remember that in a tangent line and a normal line, we call them tangent and normal. A normal is something that is perpendicular to the tangent, therefore its slope has to be negative and reciprocal. But if you notice here that these are just going to be a reciprocal, these are both positive lines. So they can't both, one can't be negative, one can be positive. But in any case, so if this slope is m, this slope right here is 1 over m. So it's actually a pretty simple process. So we just need to find the derivative. So the derivative of x would be equal to 3x squared minus 12x, right there. And then we can plug in the number. So then f prime of 1 we're looking at here. So basically what we're saying is that this is at the point 1 right here. So the derivative at 1. And that's going to be equal to 3 minus 12, which will be equal to negative 9. So all we're saying is that the derivative for the inverse function, so that's what it's asking for, find the value of the derivative of the inverse function at this point right here. So this is what I mainly want to talk about, is what is this point. But we do know the derivative at that point that it's asking for is going to be, so I'm going to say the inverse derivative at some point, which I don't know really right now, is going to be equal to negative 1 over 9. So that's what I'm saying. So we know the derivative at whatever this point is the reciprocal of that. And that is your answer. So if you look in the key, that's your answer. So it's pretty easy to find. But what I really want to clarify is what is this point that it's the derivative at, because it's not going to be at 1. So it's the derivative here, but it's going to be at b instead, and b is the y value right there. So that's what I want to make sure that you clarify. It's not that you're just finding the derivative, which is easy, but at which point are you finding the derivative at? So I'm going to plug in 1 into our original function, so f of 1 would be equal to 1 cubed minus 6 times by 1 squared minus 3, which is just going to be 1 minus 6 minus 3, which is going to be equal to 1 minus 9, which will be equal to negative 8. So that is the y value here. And then remember that these points are reversed, so then I'm really finding the derivative of the inverse function at negative 8. Now, that's not something that you need to specify in your answer. I think it's good to that you know that you're finding the derivative not at this point right here. You use the derivative at this point for your function to help you find the derivative of the inverse, but at the y value of this function, which is the x value to the inverse function. So again, probably a much longer explanation that is needed for the answer, but I don't like it when we just do things just to do it. I want you guys to know why we're doing it, and all the details around that. So hopefully this expression makes a little bit more sense. You're finding the derivative of the inverse at x equals, this is the y value. This is that y value right there, which turned out to be -8. Okay, last page. So we have here, we're just finding the derivative. So f prime of x. So we have a coefficient of 3, and then we take the derivative of the function, which would be itself times by -6, because that's the derivative of the inside function. So we get -18 e to the -6x. Alright, for this one right here, we'll take f prime of x. The derivative of 7 is 0. The derivative, don't forget that you have a coefficient of a negative value, and then take the derivative of e to the -x, which is itself, times by -1 because of the derivative of the inside. So this will just be e to the -x, because we got negative and negative right there. So then here we'll have y prime is going to be equal to 4 cosine of x, so it's going to be the function itself, times by the natural log of 4, times by the derivative of the inside, which would be negative sine of x. For 20, y prime, again, this is exponential, so the derivative will be itself, times by the natural log of 10, and then we don't need a chain rule. For 21, the derivative of a natural log is 1 over x, so y prime will be equal to 1 over x minus 2. The derivative of the inside would just be 1. And then for 22, y prime will be equal to, this is going to be 1 over x times by the natural log of the base, which would be 10, and then times by the derivative of the inside, which would be 2 right there. Okay, oh man. Before I get to 23, I'm gonna do 23 last. Okay, so for 24, y prime will be equal to, note that I just need the power rule. This is x raised to a constant, so it's really just x to the a, which would then turn out to be ax to the a minus 1. So that's the only rule I need to use here. So I'm going to drop the power, and then x raised to 1 less than the power, so that's going to be e minus 14 minus 1, which is e minus 15. Find f prime and state the domain. So f prime of x is going to be equal to 1 over x, which would be square root of 3x plus 4, times by the natural log of 5, times by the derivative of the inside, which would be 1 over 2 square root of 3x plus 4, times by the derivative of the inside of that, which would be 3. And then you can simplify, because you can multiply these together, which would just be 3x plus 4. And then so you'll have 3 over 3x plus 4 times by the natural log of 5. And you're going to state the domain of f prime. So the reason why it's asking this is to highlight an important part about the relationship between the derivative and the function itself. So here, remember that domain is just where the function, which values of x can you plug in. So what in this case I have to be careful because I have a quotient, and so whatever makes the denominator of the quotient 0, that's a domain restriction. So x in this case cannot be equal to negative 4/3, because it would make the denominator 0. Okay, now the derivative of our function though is x has to be greater than negative 4/3. So, and that's because a logarithm has to be greater than 0. So a logarithm's domain, what's inside of it has to be greater than 0. So if you take what's inside, set it greater than or equal to 0, you'd get this right here. The logarithms have a domain such that it has to be greater than 0, not equal to. So you can see that our derivative already kind of matches that. But that also means that the derivative has a domain of all real numbers. So the derivative here is all real numbers except that x cannot be equal to 4. But that doesn't really work too well with our function over here. So if this function is for example, I can plug -2 into my derivative and I can get an output, but that wouldn't make sense in terms of the relationship between the derivative and its function, is because this function right here doesn't exist at -2 or -3 or -4 or something like that, but this derivative does. So how can I calculate the slope of this function using its derivative if the function doesn't even exist? And so in this case right here, we say because of the domain of the function and the domain of the derivative, we'll just say that the domain is x is greater than -4/3, meaning that even though our derivative is defined for values that are less than -4/3, our function is not, so it doesn't make sense to include that as part of the domain of the derivative. Hopefully that makes sense. Okay, for this one, logarithmic differentiation. So I cross this out because I don't like it. So we're going to use this function right here. And the logarithmic differentiation is a method whenever we have a variable in the base and in here, because I can't use the derivative of an exponential or I can't use the power rule. So we're going to use logarithmic differentiation. So take the natural log of both sides. So that makes this natural log of y equal to the natural log of x raised to the natural log of x. With the power rule of logarithms, I can make this a product, so I can drop that to be a product. That would become natural log of x times by the natural log of x. So I'd have the natural log of y equal to the natural log of x squared, because again, I'm just going to drop this down and multiply it by right there. So there you go. Now I'm going to differentiate, and I'm going to use implicit because my y is not explicitly defined. So the derivative of the natural log of y would be 1 over y times by y prime. Okay, for this next part right here, use the power rule. I'm going to drop the 2. Inside stays the same, times by the derivative of the natural log of x, which would just be 1 over x. So then I get we'll say y prime over y is equal to 2 natural log of x divided by x times by y, so y prime is y, times by 2 natural log of x divided by x, and y is equal to, again, in this case that was the problem, so x natural log of x times by 2 natural log of x divided by x. And that is the answer. Okay, 27. A nationwide attendance per day for a certain motion picture can be approximated using the equation A of t is equal to that expression right here, where A is the attendance per day in thousands of persons and t is the number of months since the film was released. Find and interpret the rate of change of the daily attendance after 4 months. So let's go ahead and find a prime, since we're looking for the rate of change. So a prime of t would be equal to, I'm going to need the product rule because I have two functions of t. So I'll do the first times by the derivative of the second, which would be negative e to the negative t, -1 because of the chain rule, plus the derivative of the first, which would be 30t, times by the derivative of the second. And then really no need to simplify. I'm just going to go ahead and plug in 4 months. Yeah, right? So where A is the attendance per day in thousands of per person, and T is the number of time in months. There you go. So at 4 months. So A prime of 4 would be equal to 15 times by 4 squared times by negative e to the negative 4, or sorry, 4, yeah, negative 4, plus 30 negative 4 e to the negative 4. I mean, you can do some, don't have a calculator, you can just plug that all into a calculator, but essentially you have 15 times by 16, you can make that -2, and then you would have e to the 4th power, because you can, so again, I make this negative because of that, and then I can drop this to the numerator to make that positive, or in your calculator you can just type it all like that, that's fine. and then you'd have minus, what is that, 120 minus, would it be plus 120? No, would not be. Right, I don't know why I put -4 right there. That should be +4. Okay, so that would be plus. Yeah, right, that would be plus. And then e to the 4th. Okay, and then, yeah, just do whatever you need to do. Put that into a calculator. And then the average rate of change is, you could just state the number, and then it's the thousands of people per day. That's how you can describe the derivative there. Okay, this problem right here. So slope with line M passes through the origin and is tangent to the curve right here. So kind of give a visual of this right here. So here's the, let's say that we have a slope right here and it passes through the origin. Then we have another line right here and it just is tangent right here. It's tangent at some point x right there, which we don't know. And so, and then this line right here is y is equal to mx. And then this other line right here is y is equal to natural log of 5x. So what does the value of m have to be? What does the value of m have to be to make them equivalent, or to make them intersect? So if they are intersecting at this point, m will be equal to the slope of this graph, but only at this point right here. So if I can find y prime, which I can, so let's say I find y prime would be equal to 1 over 5x times by 5, which would be equal to 1 over x. So the derivative of this function right here at this given value of x will give us the value of the slope right here. So that's what we're trying to do. Find this value of x to plug into this function right here to get m. That's what we want to do. So now at this given point, since they are equivalent, I'm going to take these functions and set them equal to each other. So I'm going to say mx is equal to the natural log of 5x. Okay, it's because I'm trying to find wherever they intersect to find this x value. Okay, now the problem with this equation that we have set up is that it has the value of m before we have the value of x. So it doesn't really make sense to keep m in this equation because I don't know m without x. I need x to know m. So I'm going to replace m with the derivative because at this given point right here, they will be equivalent. So I'm going to substitute this 1 over x in for m. Since it's being multiplied by x, it's just going to be equal to 1. So I get 1 is equal to the natural log of 5x. And now it gives me an opportunity to solve for x. Remember that this x that we're solving for is this value of x right here on the x-axis where they're going to intersect. So I'm going to exponentiate both sides with a base of e, which makes those cancel. So I get e equal to 5x, and that means x is equal to e over 5. Okay, so now that I have this value of x right here where the intersection is happening, if I just plug this into my derivative of this function right here, that will give me the slope of this tangent line because that's where they're equivalent. So I just got to plug this in right there. So let's say I'm trying to find, so m, how about we say this? M is equal to y prime of e over 5, which would then be equal to 1 over e over 5, which is equal to 5 over e, or as the answer key states it, 5e to the negative 1. Whichever one works for you, works for me. Okay, I think that should cover the review. Hopefully you guys find it helpful. Email me throughout the day today, and I'll try and get to you if you have any other questions.